and we move to the next presentation given by Cesare Alfieri. He's a prototyping manager and business developer for Quantum at FEMTOPRINT in Switzerland. Hello, Cesare.
Hello, Ivan.
And Cesare will talk about integrated optical connectivity for glass quantum devices.
Very good. Thank you very much for the introduction. Now I'm going to share the presentation. Here we go. Do you see it?
Yes. Floor is
very
yours.
Good. So, thank you very much for the introduction and for the invitation to this excellent meeting. So before going straight into the topic, I want to introduce quickly FEMTOPRINT for those who do not know us. So we are a Swiss company. We are a contract manufacturer, and we are a sort of small, medium enterprise. We are more than 40 people, still growing. We're based in the southern part of Switzerland, where our headquarters is. So in the small region where Switzerland speaks Italian, but we also have offices in the French-speaking part of Switzerland and salespeople in the US. So what do? We produce glass micro devices starting from glass substrates. So our technology is 3D shaping in a negative way. So we start from a glass substrate, and then we can shape whatever shape in the end, whatever dimension in the 3D with a micrometric precision. So the resolution of our process is around 1 micron, as well as the tolerance in X, Y, and in Z. So this means that customers come to us asking to realize very complex 3D objects, and we are ready to satisfy them with these performances. Also, the aspect ratio we managed to reach is very high, around 1 to 500, and we can have very straight walls with deviations of below 0.1 degrees from ideal. And in terms of the substrates we can machine, we can have a very thick chunk of glasses up to 30 millimeters, and we can machine areas up to 300 millimeters. Even if I want to be honest, the standard is more in the order of 200 millimeters, so 8-inch wafers. So here we're talking a lot about photonics and therefore about optics. And in this case, what really matters is the shape accuracy, the resolution, but also the roughness and the surface quality we managed to achieve. So I have to say that after our machining, the surface roughness is normally in the order of some hundreds of nanometers, but we are able then to post-polish the surface to retrieve the original quality of a pristine substrate, so we can manage to have roughness below 10 nanometers. So being able to shape glass with a high degree of freedom, both at the prototyping and the mass scale production level, we are very demanded for many different applications. So we work for microfluidics, for example, but also with micromechanics. We work a lot with the watch industry, with packaging, with optics and photonics, indeed. But today we want to talk also about quantum. So where does FEMTOPRINT play a role in quantum? So we produce mainly ion traps. So this, I would say, is the main device we produce for purely quantum industry. We produce also glass devices for magnetometry, like antennas. We can produce vapor cells, and we can connect these devices both electrically and optically to the rest of the world. So this is very interesting because it matches the topic of today. And that's the reason why I want to focus mainly on ion traps and how we can add photonic and optical connectivity to these devices. So these are some examples of the ion traps we can produce out of glass. So of course, our main point is the 3D. So it's not just a surface trap. We can really manage to give the designers of ion traps an additional dimension. We can produce devices that are useful for quantum computing, but also for simulations, atomic clocks, sensors, or mass spectroscopy. What is our value proposition here? So the fact is that we can really start from the beginning. So we're not scared of low volume prototyping at the beginning. So start with an idea, but then we can really follow the customer from proof of concept up to volume production. Here, volume is shaded because at the moment I haven't seen a real volume production of ion traps, but we would be ready for that. And what can we offer here? So we can have optimized trench designs, and the trenches, for those who are not experts, are 3D features separating the electrodes. So for ion trappers, it is quite important to have insulated electrodes also after metallization and have a high density of them. So thanks to our technology, we can realize these structures that keep the insulation and the high electrode density. We can have complex 3D structures, and we can also have multi-layer traps because we are also welding glass with glass, always using our femtosecond lasers, and this allows to add an additional degree of freedom in the design of ion traps. But I also want to underline that we are heavily working and developing in the photonic connectivity market. This was originally and is nowadays mainly for datacom, driven by AI nowadays. And in this domain, we are developing mainly fiber alignment devices like V-grooves, Hall arrays for multiple fiber array units. But we can also have beam routing features, so we can write waveguides inside glass. And we can also add, thanks to the possibility of shaping glass, miniaturized micro-optics. So these are the three main building blocks, and they all benefit from the 1 micron relative positioning accuracy that we can achieve. And they can all be laser written and therefore machined simultaneously for monolithic devices. And this is very useful for optical system, for fiber to chip connectivity, and for integration into quantum devices. So just going a little bit deeper in every building block, I can show you, for example, this is an example of a fiber array unit where we can maintain a sub-micron control on the hole diameter and hole positioning. So it seems maybe not so rocket science, but it's really not trivial to have many hundreds of fiber holes that are respecting very strict tolerances at the sub-micron level and positioning. And this is quite crucial if you want to keep your losses low. So I talked also about 3D waveguides. So with a femtosecond laser focused in the glass bulk, in the volume, we can locally modify the refractive index of glass. And we create sort of a fiber in the end. It's the same refractive index difference, more or less, we can obtain in the glass. And so we have a waveguide. These waveguides at the moment are optimized for telecom wavelengths. And the reason behind that is that we need them for telecom wavelengths, as I said, for datacom. And there we have a very good positioning. We have low propagation losses in the 0.2 dB per centimeter. And the delta n, so the difference in refractive index we can induce, is not gigantic. It's in the order of 10 to the minus 2, 10 to the minus 3, and this limits a bit the bending radius. But we can have a very uniform, very nice single mode field diameters for in the order of a few microns. So here we see images for mode field diameters from 6 to 8.5 microns, we managed also to reach something below that in the very near infrared. So you have also to imagine that all this can be monolithically produced with a 3D structure around it. What we can also add are other building blocks of sort of integrated photonics, like directional couplers or multimode interferometers, and many of them are currently under development. Maybe what is not fully ready yet for the waveguides in the quantum are the wavelengths. As I said, telecom wavelengths are off the shelf now, but more interesting wavelengths, especially for ions. So I'm talking about 1760 for barium or near IR or even visible, are currently under development. So if there is someone between the audience that is interested in participating into a custom development for quantum waveguides, feel free to contact me. And finally, we also have micro-optics. So we can do refractive optical elements, for example, curved lenses, curved mirrors, but also total internal reflection mirrors and surfaces. And we can also add free-form optics. So not simply spherical lenses, but we can also have cylindrical lenses. We can have parabolic, or in the end, whatever you need. The sagittal of the lenses can be below 10 microns. And yeah, we can have multiple optical elements fabricated in a single production step. The shape deviation can be lower than 1.5 microns. So recent development also in our metrology allowed us to say that we're, for most of the cases, below 1 micron. And after several iterations that we can have with our customers guiding us also through functional tests, we can also reach below half micron of shape accuracy for our refractive optical elements. So heading to a conclusion, what we can envisage in this world are glass microcones. So you can imagine to have a very precise hole, that's what we call a glass ferrule, that is matched with a waveguide. We can also have free propagation in glass. But let's think we need a waveguide. We can have them with very good performances in terms of propagation losses, coupling losses, and low crosstalk, even when the pitch is very small, so a few tenths of microns. And then we can have optical surfaces for mirrors, so to manipulate the beam. So in free form, in conventional shapes, this is possible with the shape accuracy I mentioned before, with surface roughnesses that can go below 10 nanometers. And all of this can be integrated within a purely quantum device like an ion trap. So this can, we believe, bring a real and solid benefit to the quantum world that we heard already many times today is struggling with packaging. So imagine to have a more compact and integrated device is for sure an advantage. And with this, I came to the conclusion of my presentation. I will be very happy to answer your questions.
Very nice presentation, Cesare. Very nice capabilities with your laser processing. I actually wonder, can several of those processes, so for example, making the glass ferrule, making the waveguide, and shaping the connector that you've just shown us, can all of that be done inside one setup with the same laser?
Yeah, exactly. So the idea behind that is really the monolithic approach. This will reduce significantly the relative misalignment between the single components. Of course, there are maybe some limitations that we discussed design by design, but in principle, yes, that is possible. So we could have a waveguide, a fiber, as I showed in the last slide, a free-form optical surface integrated into an ion trap to facilitate the ion dressing, for example.
Oh, that's very impressive. Okay, Mirwais, please.
Yeah, I will have a bit more technical question instead. So I saw this very nice where you did directed the light down. The question, because you had the very nice slot for the fiber also. This requires both etching and writing. Do you do that together in one process? I think I want to follow up on Ivan's question. So, or do you separate?
Yeah. So I didn't want to go too much into the detail for a lack of time of our process, but our process is a two-step process. So we start with a laser writing. We start from a glass substrate and we focus the femtosecond laser inside the volume. This is like a spot, a pen that defines the shape. By defining the shape, we induce selectivity against a wet etching solution. And the second step is we put the glass into the etching. So the laser is not removing any material, it's the chemical etching that is removing the material. So it's a two-step process, but all the features are then written and etched together. And this preserves the alignment and the accuracy.
Okay, I was just going to compliment on that, but good you say that. Thanks.
Okay, if there's no further questions, let's thank Cesare for an impressive presentation again.